galaxy connection at very low masses.
Okay, thank you, everyone. Can you hear me? I think it works. Well, before I begin, I want...
Yeah, maybe move it up.
Okay. It's better now? Even higher. Okay. Sure. Okay, good. Then I'd rather whisper. All right. Well, before I start, I would like to thank the organizers and everyone who's involved in making this exciting workshop happen. Okay, so I'm going to talk about the Galaxy Halo connection, and as a starter, I should maybe talk about Halo assembly bias. So Halo assembly bias is a dependence on the clustering of halos at a given halo mass on a second parameter that's not halo mass, okay? And that's typically something related to the halo assembly history, for instance, the halo concentration, the halo formation time, and things like this. So the actual bias signal that you get may depend, or what does depend on this secondary parameter. So for instance, it's shown here from a work by Risa Wexler, that the halo concentration, the halo spin shows a larger bias signal at the high mass end, and the halo formation time shows a larger signal at the low mass end. So the question that one can therefore ask is, since this has been seen in dark matter simulations for halos, does a similar property exist also for galaxies? So in particular, do galaxy properties at fixed halo mass also depend on the halo assembly history? Okay, so that's the kind of question that I want to talk about today. Now, we do expect that there is some kind of connection between galaxies and halos, of course, at some level, just based on how galaxies form out of these of density fluctuations that grow and then collapse, right? And then the gas that sits either within these halos or sits around it cools and forms the galaxies at their centers. Okay. Now, this was a simple picture. Of course, in reality, it's a little bit more complicated. There's lots of additional so-called baryonic physics in there, such as cooling, hydrodynamics, also radiative transfer, star formation, etc. And the feedback that comes from the star formation in particular has the property that it can, so that essentially small scales can affect large scales, right? And that makes it a very nonlinear and very complicated problem. All right. Now, so why do I talk about low-mass galaxies or dwarfs, right? And there are a couple of reasons. One is, well, they're kind of interesting objects. The baryonic process here are particularly good effective, so they're kind of interesting objects to study. The galaxy halo connection is actually not very well explored at those low masses. And that is because it's actually very difficult to measure halo masses for these low-mass galaxies. As I mentioned before, the bias that is related to the halo good assembly is often larger at low masses, so here we may actually find a stronger signal. And of course, I mean, as we heard in the previous talks, dwarf galaxies are also a very good laboratory to study dark matter, right? They have typically high dark matter fractions, except maybe one galaxy, and they are a source of classical problems, like the too big to fail problems we just heard about. Okay, so how do we quantify the galaxy halo connection? And one way to do this is with the stellar mass halo mass relation, right? And I'm sure you've all seen this kind of plot. Essentially, what we want to know is what is the probability that the galaxy has a certain stellar mass as given its halo mass, and we dumb it down a little bit by just talking about the average relation, and then by talking about the scatter around this average relation. And the scatter is about of order 0.2 dex, and as I said, it's not actually that well known for dwarfs. Another thing that's maybe quite interesting in this context is, does the star formation rate of galaxies depend on the halo growth rate or on the halo formation time? Right? And there have been some models that have been arguing for this kind of dependency, such as good age matching or some work that I've been involved in, of cosmological starvation. Okay, so why do we want to understand this? Okay, well, first of all, it tells us a bit more about how galaxies form, right? We learn how how galaxies form inside these dark matter halos. It's possible, if you have a model, to constrain something like the cosmological parameters. So if you have like a better understanding of how this galaxy halo connection works, we can then use, essentially, we can look at the observations of galaxies and then infer what are cosmological parameters or what are possible dark matter models. Okay. Of course, a big caveat here is that we need to understand this galaxy halo connection, and we need to understand such a galaxy formation to do that well. Okay, so how is this done in practice? Well, we have different models to do this, right? And they go from very good empirical models like HUD models to the most physical models, which are hydrodynamical simulations in a fully cosmological context, where we essentially throw everything we have and we know at the simulation. And that's what that's the kind of path or the kind of approach that I've been taking, and I'm going to talk about kind of results that are based on such cosmological hydrodynamical simulations. It's called the Massive Fire Project, and it's part of the Fire Project. And so this is like a suite of cosmological hydrodynamical simulations. They run down to redshift 2 and contain about 40 or so massive halos and massive galaxies in these massive halos, and then thousands of lower mass galaxies. So and here by low mass galaxies, I mean something between with halo masses of 10 to the 9 to 10 to the 11. Okay. The numerical resolution is great for the simulation of these massive galaxies, but it's there are definitely better simulations now out there that study individual dwarf galaxies. Right? So the physics is just the standard fire physics in here for the aficionados. That's all fire 1. Okay, so it's star formation, and there's feedback from supernovae, from stellar winds, and so on. A few of the results from massive fire. So this is the stellar mass to halo mass relation as predicted by the massive fire simulations, and they agree relatively well with observations. I mean, here we have essentially good empirical constraints from abundance matching, and these are essentially predictions, right? I mean, this is just an extrapolation, so these lines are just extrapolations of the abundance matching predictions to lower masses. And also here on the right side, I show the star forming sequence as predicted by the simulations. You should only look at the blue points, okay? And you can see, yes, they are about in the right range. The scatters may be slightly larger, but it's not maybe too bad. Okay, so now what I want to kind of show you is these relations again, but where I now bin it according to different halo properties. And I show you one where I bin it according to halo growth rate, halo concentration, half mass redshift, and 5% mass redshift of the halos, okay? Yeah, so this one here is just like a smooth version over all the galaxies in the sample, okay? So let's do the binning for this one first. So that's how it looks like. So the way to read this is so the first quarter is the 25% of halos with the lowest value of this, so with the lowest halo growth rate. And you can clearly see that these guys have higher stellar masses and lower specific star formation rates than the 25% of galaxies that live in halos with the 25% of the highest halo growth rate. Yes?
Are these rates today, like growth rates today?
It's all a redshift 2. Everything I show you is done at redshift 2, yes. So, and I'm happy to tell you how I measure the growth rate. Well, actually, I have a slide later on, and I can show you this. Okay, so let's look at what happens for the other halo properties, because that's also quite interesting. And it looks like this, right? So, well, okay, first of all, you notice that the colors are inverted, which makes sense, right? Because now the first quarters means the lowest halo concentration, right? It's probably the ones that are most recently formed. So they have the lowest stellar masses. As far as halo concentration doesn't appear to be doing too well when it comes to showing like a spread in the specific star formation rates. yeah, and those two properties you do somewhat better. But the trend is more or less the same. Okay, so actually, how to measure growth rates? Well, this is, for instance, this is the halo. This is halo formation history of one particular halo. It's fit with a particular function, and then essentially I get the halo growth rate from the fit, right? And it's the halo growth rate at this time at redshift 2. And it's also normalized to the growth rate of the average. Okay, so 1 just means, so if this parameter 1 means this halo is growing like a similar halo of this mass at redshift 2. If it's 2, it means it grows twice as fast. Okay, so that's, for instance, a very quickly growing halo that has this I of 2. Okay. So then what one can do is, of course, one can play a few games. One can fit the halo growth, the stellar mass to halo mass ratio as function of the halo growth rate. Oh, I'm very good in time. So what one finds when one does this is that the stellar mass at fixed halo mass scales approximately like this with the halo growth rate. Okay, so the faster a halo grows, as I showed you before, the lower is the stellar mass at a given halo mass. Okay. Okay. Then when we look at the specific star formation rate, when I look at the specific star formation rate, the picture is slightly different. The specific star formation rate increases with the halo growth rate. Okay. With a slope of about 0.1. You may notice these kind of dashed curves in here. These are not fits to, so these are not actually good regression fits or anything. This is like, so this is a prediction of a toy model that is somehow fit to the simulations, but not actually to this. So I have to talk about this afterwards. But the point is that this toy model does kind of reproduce the general trends that you see here in the simulation. Okay. And now this is maybe the most interesting, the star formation rate, or maybe not the most interesting, but the most surprising to me at least. The star formation rate does not scale, or if anything, it slightly decreases with increasing halo growth rate. So halos that grow fast or somewhat have, at fixed halo mass, have a constant star formation rate, or even slightly lower star formation rate. Okay. If you fit it at constant stellar mass, okay, then you find again that, this behavior. But again, this is essentially this is fully consistent with this and the previous slide that I showed. So that's just confusing to you. The more important point is at fixed halo mass, a galaxy that has a faster growth rate does not have a higher star formation rate. Okay, and I can explain this. Okay. All right. Anyway, so these trends hold over the broad kind of range of halo masses that I explored in the study. And so clearly halo growth rate is an important second parameter, at the very least for the stellar masses of galaxies and for the specific star formation rates. All right, so now why? Okay, good question. So here on the left, I show this kind of model that I showed you before a little bit, okay? And on the right, I actually show, I took essentially I split my sample again into 4 different bins. These are like the top quarters. Essentially, first of all, I make a mass selection so that the halo mass is about 10 to the 10 at redshift 2. And then from those, I took like the top 25% and the bottom 25% in terms of the halo growth rate. And these are the 2 bins, okay? So these are the slowly growing ones, and these are the quickly growing ones, okay? And that's the model prediction, so just that you could compare that they look actually similar, although of course not identical. So, okay, so the halo mass, okay, of course, they have to be identical here, that's by definition. Now, the cold gas mass in the simulations are also the same, okay? So even though these halos grow faster, they have exactly the same cold gas mass than the halos that grow, or the galaxies that don't grow very fast. By cold gas mass here, I mean the cold gas mass in the galaxy. So this is essentially measured within 10% of a Ver, excluding all satellites. Okay, the star formation rate, well, you see some slight difference. If anything, the fast-growing ones have a slightly lower star formation rate. And the stellar masses are much lower, okay? And so the reason is very simple. So the gas mass is similar. Star formation rate, which depends on the gas mass divided by depletion time, has to be similar. Now, because the star formation rate was much lower in the past, because the tails were growing quickly, they were less massive in the past, had lower star formation rate in the past, they have now a much lower star formation rate. They have now a much lower stellar mass, okay? So this makes perfect sense. And the specific star formation rate is higher, not because the star formation rate is higher, but because the stellar mass is lower, right? So if you divide this by this, then you get this, okay? So this explains these findings. Now, what are the implications of this? So there are two implications that I want to talk about, namely for the scatter of the stellar mass-halo mass relation and for the scatter of the star-forming sequence. Now, we know these scatters are, relatively small for this one, at least for the massive end. As I said, we don't quite know this. These are kind of predictions of hydrodynamic simulation, so maybe the scatter increases to about 0.3 for like halo mass of 10 to the 11 or so. It's not quite clear. The star-forming sequence has a much larger scatter. It's not very strongly mass dependent, of about 0.3 dex. All right. So now what I did is I ran some dark matter large volume simulations to actually measure the scatter of this psi thing, okay? And it turns out it's about 1. So the scatter is about 1, and it's not very strongly mass dependent. Okay, so these are two different simulations just kind of stitched together so that I can actually span a larger range in halo masses. It's just 1. It's just the scatter of this quantity psi. Okay. Yeah. No, psi is the halo growth rate normalized to the average. Okay, so it's just like it's just a normalized kind of version of it, and that's just the scatter. Okay, and it's about 1. Maybe you can argue maybe it's 0.8 or whatever, but it's a order unity. So now, if you combine this with these scalings here, we find that we predict, or that I predict, the scatter in the stellar mass-halo mass relation has to be of order 0.2 dex. Okay, and that's similar to what's observed at the more massive end. And the scatter that I would predict for the star-forming sequence is of order 0.1 dex, and that's much lower than is observed. Okay, so the conclusion is that the variations in the halo growth rate, they have definitely the potential to explain a large fraction or maybe all of the scatter in the stellar mass-halo mass relation, but they are definitely insufficient to explain the scatter in the star-forming sequence. Okay? All right, that's the summary, and happy to take questions. Thanks.
Okay, Joel.
In a paper led by
Mhm.
we analyzed the scatter and the accretion rate in a bunch of large box simulations, full-thread quant, multi-dark quant, etc.
Right.
What we found was that the scatter is about 0.3 or 0.4 dex, independent of mass and redshift. I can't tell. Is that consistent with what you're finding? Are you
So,
aware of our paper?
of course, I'm aware of your paper, and
Are you in agreement? Or
think I'm in disagreement because the main result of this paper was, right, that you said the scatter of the star-forming sequence for star-forming galaxies, right, but essentially the argument is the scatter of the star-forming sequence is related to the scatter in the halo growth rates, right? Exactly, and this would say that's not sufficient. So the scatter that you have is not sufficient that I get.
But just getting back to the question of the dark matter.
Dark matter
Yes.
itself.
Oh, well, that's actually large. It's huge. As you saw, the scatter in the accretion rates itself is actually larger, right? So, I mean, of this normalized version. I mean, so the thing is this.
These are
Yeah.
very big, very carefully done simulations. Are you saying that they're wrong?
I'm not saying they're wrong.
Then how can you disagree?
Well, it's a very different quantity, right? So you measured what exactly is the halo growth rate that you're referring to, right?
The units are different, that's why I'm trying
Yeah, that's
focus
what
on
I'm-
the.
Yes.
That's what I'm trying
So
to-
that's a linear quantity. It's really just the growth rate.
But if you express this.
And I
as
was-
scatter
yes.
and the growth rate the way we did.
So,
Excuse
yeah.
me, plus or minus 1 is plus or minus a factor of 2, it's plus or minus 0.3 dex. So it might
Is
agree.
that what you mean? This is
Yes.
0.3 dex? In that
No,
case,
well, I'm not sure that's
Not
what I'm
quite
saying,
expressing
but
it that way. But
yeah.
Don't jump to conclusions.
Well, that's
what
why
I'm
I'm
trying to say.
asking.
I'm happy to sort this out good afterwards, but I think it's maybe that's best if you talk about this afterwards, yeah. Okay, maybe here?
Well, I think it's known observationally and for
Mhm.
simulations that's known as stable mass dependent on environment quite
Mhm.
strongly. I think these known as massifier central.
Yeah, so these are
Bias
correct.
relevant or not?
Yes, yeah, absolutely. That's a very good question. So I'm only showing you results for massifier centrals that are also non-splashbacks. So I excluded everything that is a satellite or has in the past been a satellite. If I would include those, it changes things, right? So yeah, so there's a very strong effect of, so these guys look very different. So if you include splashbacks or satellites, yes.
I think that's mentioned that scatter in a primary can be derived analytically from chaotic dependent perspectives.
Mhm.
I think that we get up to the matrix dependent.
Okay, that's cool. Great, thanks.
Okay, let's do one more. Okay, dude.
Well, that's possible. I mean, if I change the feedback, definitely what changes is the stellar mass to halo mass relation itself. And so I would expect it. I mean, to some extent, it's also a bit tricky because the scatter that you measure, right, it depends on the slope, right, to some extent, right, because you're averaging over bins, and so if it's steeper, then you get automatically somewhat of a larger scatter. So I would expect the answer is yes, to some degree. I can't really quantify by how much.
Thanks very much.